I'd like to thank the organizers of not just this conference for inviting me to give a talk, but everyone else who has been involved in organizing this stimulating extended program for 4 months. So this is work done with Eric Hanson, who unfortunately couldn't be here today because of some visa problems. And he's a joint PhD student in Cambridge and in the University of Paris. So I will be talking about a surprising majorization relation and its applications. So let's quickly recall majorization, which surely all of you know about. So as you know, it is a powerful mathematical tool which has found applications in many different fields. So mathematics, probability statistics, calculation of variation, physics, mathematical biology, economics, and of course, quantum information theory. In fact, I came across this very interesting paper by Barry Arnold, whose title is Majorization, Here, There, Everywhere. So as far as quantum information theory is concerned, you find applications of majorization in entanglement theory, uncertainty relations, quantum thermodynamics, and others. So as you know, majorization is a partial ordering of vectors. So given two vectors x and y in Rd, we write x majorizes y, denoted in that manner, if and only if the following inequality holds. So here, xi's with the down arrow are the elements of x arranged in non-increasing order, and similarly for the y's. And of course, equality holds when k is equal to d. And it's a partial ordering in the sense that if x is not majorized by y, then that does not imply that y is majorized by x. In fact, it could happen that x is not majorized by y and y is not majorized by x, in which case you say that these two vectors x and y are incomparable. Another basic fact about majorization is x is majorized by y if and only if x can be written as a convex combination of permutations of the elements of the vector y. And hence, if x is majorized by y, then x is more disordered than y in this sense. A particular class of functions which are of particular relevance in majorization theory are the Schur convex and Schur concave functions. So just to recall, a function f from Rd to R is said to be Schur convex if it preserves this ordering. So x majorized by y implies f of x is less than or equal to f of y. And it is Schur concave if minus f is Schur convex. So, sorry, this came a little too early. But if you consider two states, now let's look at majorization in the context of quantum information theory. So we consider two states, rho and sigma, acting on a finite dimensional Hilbert space. So here, d of h is the set of all density matrices acting on h. Then we say rho is majorized by y and denoted like this if the corresponding vectors of eigenvalues of rho and sigma satisfy this majorization relation. Now, any two arbitrary states, just pick any two arbitrary states. There's no reason for them to satisfy any sort of majorization ordering. So we could have rho is not majorized by sigma and sigma is not majorized by rho. And it is this fact which makes the result that I'm going to state surprising. So in order to state what the result is, I need a little bit of notation. So in this case, we say the states are incomparable. And let rho be a state. And choose an epsilon, which is a parameter in 0 and 1. And you consider a ball of states centered around rho, the ball being taken in trace distance and of radius epsilon. We call it the epsilon ball in trace distance. Then the theorem, the first theorem, is that there exists two states, rho upper star epsilon and rho lower star epsilon, in this ball, such that the following relation holds. So this is indeed surprising because what we find here that this rho upper star epsilon is majorized by every state in this ball. And on the other hand, the rho lower star majorizes every state in the ball. And these states we construct explicitly. And in particular, if rho is a pure state, that state is a pure state, and the corresponding rho upper star, which we call psi star epsilon, has this very familiar distribution, which I think many people call the L-shaped distribution. So this is theorem 1, and it is in this particular paper. But it was also independently obtained by Michal Horodecki, Oppenheim, and Sparaciari. And what I'd like to say, it is not just a surprising result, it is an interesting and useful result too. Okay, so I will quote this theorem just in this short form again and again in the forthcoming slides. So let's first look at an immediate implication of this result. So consider a Schur concave function now from the space of density matrices to the reals. So this is the definition. And an example is the von Neumann entropy. It's known to be Schur concave. So let's look at this part of the majorization relation. Rho star epsilon is majorized by every state, other state omega in the ball. So the Schur concavity of the von Neumann entropy therefore implies this relation. So immediately we see that rho upper star epsilon is the maximum entropy state over this ball for the von Neumann entropy. Similarly, if we look at the other majorization relation, then since rho lower star epsilon majorizes every omega, then this relation holds. And therefore, we see that this is the minimum entropy state over this ball. And this is not just a question of being a maximizer and the minimizer of the von Neumann entropy, but it is a maximizer over b epsilon rho for any Schur concave function. And similarly, this is the minimizer, because the only thing we've used here is the Schur concavity of the underlying function. Okay, so this is the outline of the rest of the talk. I will actually first start with an application. And the application is the statement of a local continuity bound for Schur concave functions. And then we'll go on to a discussion about the states. First, I'll talk about a few interesting properties of the rho upper star epsilon. Then I'll try to give you some geometrical insight into these states, and followed by the construction of the rho lower star, and then that of the upper star, which will be motivated by a more general result, which we think is of independent interest. And then I will talk about some further applications, uniform continuity bounds for a family of entropies, approximate LOCC conversions of bipartite pure states, and expressions of entropies arising in one-shot information theory. And then if I get the time, I'll have to give the summary and open problems and the story behind how we started working on this problem. So let's start with the local continuity bound for Schur concave functions, the application I talked about. In particular, let's consider the case of the von Neumann entropy, and let's recall what is known regarding its continuity bound. So what do we continuity properties. So what do we mean by that? So you take a parameter epsilon in 0, 1 and two states rho and sigma, and such that they are epsilon at most a distance epsilon apart in trace distance. Then the question is, if these two states are close, how close are their von Neumann entropies? This is what one wants to find. Now this the bound for this is now called the Audenat-Fannes bound. It was first bound by Fannes and then strengthened by Audenat. And I'll use the acronym AF for it. And this is the bound, that if epsilon is less than 1 minus 1 over d, then this bound is satisfied, where that's the binary entropy. And if epsilon is greater than 1 minus 1 over d, then it's just log d. Of course, one can ask, when does equality hold in this bound? Now, without loss of generality, let us assume that S of rho is greater than or equal to S of sigma. Then equality holds for this case if sigma is pure and the state rho has a vector of eigenvalues given by this familiar distribution we just saw before. And for epsilon greater than 1 minus 1 over d, again, equality holds if sigma is pure and rho is the completely mixed state. Okay, now the point is such a bound is a global or uniform continuity bound in the sense that it depends only on d and epsilon. It does not depend on any other properties of the states rho and sigma. But there could be a situation, very often one encounters a situation where one of the two states, rho and sigma, is known. For example, consider the case of data compression and say rho be the source state which we want to compress. And let sigma be the state we obtain after our compression-decompression scheme. So in this case, we know properties of rho. And using this information, one can get a sharper bound than the Lsigma-Fannes bound. And this bound we will denote by star, and it lies here. And because it depends on the spectrum of rho and the properties, so we call it a local continuity bound. And this is what we obtain from our majorization relation. Okay, so let me see how, let me just show you how very simply from the majorization relation you can get such a bound. So we saw that rho upper star was the maximum entropy state and rho lower star was a minimum entropy state. So if S of rho is greater than S of sigma, remember this is the quantity we are trying to bound, we can write it like this, which of course we can write like this. And the minimum entropy state was the lower bar, so we can replace it by this quantity. Similarly, in the other case, when S of rho is less than or equal to S of sigma, we can write it in the following manner and replace S of sigma upper bound by the maximum entropy, which was S of rho star epsilon, because that was the maximum entropy state. So from these two relations, in general, we find an upper bound given by the maximum of these two quantities. This is the local continuity bound. See, it depends on rho, and we find that this is less than or equal to the Lsigma-Furness bound. Okay, so I summarize it in the next slide. So let epsilon be a parameter in 0, 1, and rho is a state. Then for any sigma, which is at a distance at most epsilon from it, the difference is given by this local continuity bound, and which is upper bounded by the global or uniform Lsigma-Furness bound. And in fact, this inequality is strict whenever rho and sigma are mixed states. And in fact, equality holds only if rho and sigma satisfy the equality conditions for the Lsigma-Furness bound, which I gave before. Now, this bound, what is nice about this bound is, as you will see, these two states that I talk about can be computed explicitly. So you can find this bound very easily. And this is not just a bound for the von Neumann entropy, not a continuity bound for the von Neumann entropy only. We can replace the von Neumann entropy by any Schur concave functions, and we get a local continuity bound from our majorization relation. Okay, so let's go to the next bit. Let's start talking about the states, and let's first state some of very interesting properties of rho upper star epsilon. Firstly, we see that this is a unique state. It's a unique state in this majorization ordering, and therefore a unique maximum entropy state in this ball. Also, it can be easily shown that it commutes with the state rho, and it satisfies an interesting semi-group property. If lambda epsilon is the map which takes rho to this rho upper star epsilon, then such a relation holds. So here epsilon 1 plus epsilon 2 both take positive values, and their sum is less than 1. And we use this property later on to prove a uniform continuity bound. And also interestingly, it saturates the triangle inequality for rho and for the completely mixed state. So pictorially, if this is the completely mixed state and this is rho, you have something like this. So it lies on the straight line connecting rho with tau. This also has a particular significance, which we'll come to later on. Okay, so let's quickly go through the proof of uniqueness, because it's very, very simple. So rho star is the maximum entropy state. We want to say that it's a unique maximizer. To do so, let's assume the contrary. Let rho upper star and rho tilde upper star be two different maximum entropy states. So their von Neumann entropies are equal, and let that value be equal to S. Then, if you take a convex combination of them, by the convexity of this set, they will also belong to this ball. And as a result, the von Neumann entropy of this state is just this, which is greater than this. Why? Because of the strict concavity of the von Neumann entropy. And this is, of course, a contradiction, because we said S was the maximum entropy in that ball. Okay? And therefore, we infer that the rho upper star epsilon is indeed a unique maximizer, not only of the entropy, but of the maximum of the von Neumann entropy. Sorry. So, before stating what the construction behind the states is, let me give you a geometrical insight. So, to find the states, actually, rho upper star and rho star, it suffices to restrict attention to the classical case of probability distribution on D letters, where D is the dimension of the Hilbert space. That is because this majorization relation is actually a majorization relation between these vectors of eigenvalues, which are probability vectors, right? So what we do, therefore, in constructing these states is instead of considering the density matrices on H, you go over to the probability simplex, okay? And for d equal to 3, as you all know, this is the probability simplex. And let R be the vector of eigenvalues of rho. And instead of a ball around rho, we consider a ball around R, which in this case is given by this hexagon. So this is the definition of the ball, okay? So finding rho upper star and rho lower star such that this majorization relation holds, then reduces to finding two probability vectors belong to this probability simplex, belonging to this ball in the probability simplex, such that the following majorization relation between these probability vectors hold, okay? What happens then? That these probability vectors serve as eigenvalue vectors of rho upper star and rho lower star. So we saw this, that for any R point belonging to the probability simplex, the ball around it is a convex polytope. So just to get a feeling of what these states might be, let's ask a question. Let's take a point in this ball and ask, could it be a possible candidate for R rho star epsilon? Okay. So what do we do? Now let us consider for the point Q, let us consider the set of probability vectors which are majorized by it, the set of all probability vectors in the probability simplex which are majorized by it. Now it is known from Birkhoff's theorem that M of Q is the convex hull of permutations of Q. So this is the symmetric group. So now we want a candidate, we want to ask whether Q is a candidate for R lower star epsilon, which satisfies this relation. So that means what? If you have R lower star epsilon, the corresponding M R lower star epsilon must contain the entire ball, yeah, all the vectors in the ball, because all of them are majorized by R lower star epsilon. And now we are in a situation to immediately answer this question. The answer to the question is no, because if you consider the convex hull of it, it's given by this green figure, and you see it does not include that part of the ball. Okay, so this is not a good candidate. So MQ does not contain the entire B epsilon R. So Schur concavity of the Shannon entropy tells us that once again R star epsilon is the point on which H omega is minimum, because that was the minimum entropy state. Now that's a concave function, and this is a convex set. So our first trial gave us a negative result, but there is the principle called the minimum principle, which tells us that in this sort of scenario, the minimizer lies on the boundary of this ball. And since B epsilon R is a convex polytope, it lies on one of its vertices. And we find that it is in fact this vertex which is the minimum, and which respects what we required, that its convex hull should contain the entire ball. In fact, this minimum principle yields a simple solution to the problem of minimizing the Shannon entropy over B epsilon R, and thus allows us to find rho lower star epsilon R, because that once we know its eigenvalue vector, we know the state. So now I can give you cleanly the construction of this rho lower star epsilon. So this is just what I said. It suffices to construct this R lower star epsilon, which satisfies this majorization relation in the classical case. And then any state with this eigenvalue distribution is a valid candidate for R lower star epsilon. R lower star epsilon is not a unique minimizer, so it could be, there are unitarily equivalent states which all act as minimizers. So what do we do? Let me tell you the explicit construction. So let R be the this vector such that they're already ordered. Now, if the smallest eigenvalue is greater than epsilon, then all we do is this. We raise the largest eigenvalue by epsilon and lower the smallest eigenvalue by epsilon. And that will be your R lower star epsilon, as simple as that. But if Rd is not less than or equal to epsilon, then you consider the smallest L eigenvalues such that their sum is greater than or equal to epsilon. And now, once again, what we do is we raise the largest eigenvalue, and all of those we lower to 0, and the one above it we lower to in this manner. So there is this extra, what we have, we can play around with this quantity epsilon, and we move it up or down accordingly. So this is what happens when Rd is greater than epsilon, and this is what happens as Rd is less than epsilon. So Horowitz called this state the steepest state, which makes, and the reason behind it is because we want to consider the minimum entropy state. Remember, our lowest star epsilon was the minimum entropy state, and it is the state closest to a pure state, and which has the steepest eigenvalue distribution. But we want to go closest to a pure state in this ball, and this is the way you do it. Okay, now let's look at the more interesting case, that of rho upper star epsilon. And I'm going to motivate it by a more general result, which I think is of independent interest. Okay, so recall what we saw in the earlier slides. We saw that rho upper star epsilon is a unique state, and I didn't prove it, but I told you that it was diagonal in the eigenbasis of rho, with eigenvalue distribution given by R upper star epsilon, where R upper star epsilon is majorized by every other state in the ball on the probability simplex. Now, to find this R upper star epsilon, it is not just a matter of checking, even in this little example, the values at the vertices. Okay? For the example considered, numerical computations yield that it is not even a vertex, it is a point here. So, however, useful insight into what that R upper star epsilon could be, in fact, and hence into the state, it can be obtained via convex optimization theory. And you recall that it is an optimization problem. It is optimizing the Schur concave function over the ball. And our characterization of rho upper star epsilon originates from the following more general result, which is rather interesting and might have some follow-on work. So what is this more general result? So we consider a class of functions. So a class of functions going from density matrices to the reals. And I'm going to specify it shortly. And the interesting thing is that this Hilbert space H could also be the Hilbert space of a bipartite system. So it could be H8 and HB. So we are stepping away from what we were considering and now looking at a more general problem. So in a nutshell, what we proved, this more general result, is that if you're given a state rho and this parameter epsilon and a function in this class I'm going to talk about, we obtain a necessary and sufficient condition under which a state in this ball maximizes f. So I'm sure you can see why this is related to the problem I'm considering. And what is interesting is we use a result way back from the 17th century, which is called Fermat's rule of convex optimization, in order to prove this result, which I'm going to state. So in order to prove this, we need a few things. So to specify the class of functions, we need to introduce certain concepts. First is that of Gateaux-differentiability, the Gateaux gradient of a function, and the concept of subgradients. I was also going to talk about Fermat's rule itself, but I thought I wouldn't have the time. If I do, I'll do it on the blackboard. So Gateaux-differentiability is just the extension of the idea of directional differentiability to an arbitrary real vector space. So consider real vector space V with inner product denoted like that. And let f be a function from the vector space to the reals. And now we consider the direction and derivative of x in the direction h, where x and h are elements of this arbitrary real vector space, is defined in the following manner. And if the map phi of x, which takes h to this f primed x of h, is linear and continuous, then f is Gateaux differentiable at x belonging to V. And Gateaux gradient of it is denoted like this. It is just the dual to phi of x in this inner product, with respect to this inner product. So delta nabla f of x, h is phi x of h. So this is the Gateaux gradient. That was Gateaux differentiability, and we'll talk about classes of Gateaux differentiable functions in a minute. These include the von Neumann entropy, the Renyi entropies, and the conditional entropies, for example. But let's move on to the next thing that we need, which is subgradients. Now, if you look at differentiability as of a function as the existence of a linear approximation at a point, and generalize it by defining a linear sub-approximation at a point, then we arrive at something called the subgradient. So the definition is the subgradient of a function going from this vector space to the reals at the point x is given by this set. So it is the set of all vectors u such that fy minus f of x is given by this for xy belonging to v. Now, why is this a linear sub-approximation? Why did I use that word? So let us consider the simple case when v is just r. Now, and let us look at this inequality. So this just reduces u times y minus x. Therefore, u is less than equal to this. That's why we call it a linear sub-approximation. So what is nice, now let's relate these two concepts. If you have a convex function, then f is Gateaux differentiable at x. If f is Gateaux differentiable at x, then the subgradient has a single element, is a singleton, and that single element is its Gateaux gradient. And this is what really helps us in proving the result via Fermat's rule. And Fermat's rule gives us a characterization of the minimizer of such a function. It says that x is a minimizer if the subgradient is equal to 0, which is the 0 vector. Now, if we talk about Gateaux differentiable function, that just amounts to proving that the Gateaux gradient is equal to 0. So that's how the Fermat's rule comes into play. Now, how will we apply these concepts to the problem at hand? So we consider the real vector space to be B of H, linear operators on H, and as an inner product, we take the Hilbert-Schmidt inner product. And so for x belonging to V, we now consider states belonging to B of H, in fact, to D of H, the density matrices. And we consider functions from D of H to R. And the relevant Gateaux differentiable functions on positive states are the von Neumann entropy, and let's just highlight this, because for it, the Gateaux gradient is very simple. It is minus log rho minus identity. And the Renyi entropy of parameter alpha and the conditional entropy. So these are all examples. Okay, but this is the only thing we need to take on for the remaining slides. Okay, so what is the more general result? Given a state rho and a parameter epsilon and a function f in a class f, which I haven't told you yet, a state sigma belonging to a ball around rho maximizes this function if and only if two conditions hold, this or this. Now, I'm going to tell you everything step by step. We'll go over these conditions in detail. And the whole purpose, why am I talking about this theorem, is we want to see how this theorem gives us an immediate clue of how to construct the rho upper star epsilon, which was the maximum entropy state, or equivalently, the minimum state in the majorization ordering. Okay? So what are these different quantities appearing here? First quantity, what is this function, class of functions f? It is the class of concave, continuous, Gateaux differentiable functions. Okay? And we saw examples of it in the last slide. Then what is pi plus minus? So what we do is we take the difference operator sigma minus rho and write it in this manner. So please don't confuse it with the probability simplex, which we've left behind. And pi plus minus are just orthogonal projections onto the supports of delta plus and delta minus. What is Lsigma? Oh, I've just used Lsigma to make life simple for me. Myself, it is just a short form for the Gateaux gradient of the function. Yeah, instead of writing this, I've just written Lsigma. And what about this quantity? Lambda plus and lambda minus are just the largest and smallest eigenvalues of Lsigma. Okay? So let us look at it in detail and see what is the significance of this result. So what are we looking at? We are looking at under the conditions, necessary and sufficient condition under which a given state sigma is a maximizer in the ball around rho. And so let's pick up the first condition. So remember in what we had done before, we'd call the maximizer rho star upper star epsilon. So in the slide, you should look at sigma as rho upper star epsilon. It's the same thing. So the first clause of the theorem says it is a maximizer if number 1 holds and number 2 holds, but let's come to number 2 later. Number 1 says either sigma is equal to I over d or this is equal to epsilon. So let's interpret this. That means we call tau to be the completely mixed state. So either the completely mixed state belongs to the ball, in which case it is the maximizer and it is the unique maximizer, or it does not belong to the ball, in which case this holds. That means the maximizer sigma, which is same as rho upper star epsilon, lies on the boundary. Okay? So this is what we get from the first clause of the theorem. Either it's the completely mixed state or it's a state lying on the boundary. But in that case, what is the state? We don't know it yet. And that is given by the second clause of the theorem. So let's look at the second clause of the theorem. It was written like this. Okay? So what does this tell us? So let's look at it carefully from the perspective of the von Neumann entropy. So remember this L sigma was the Gateaux gradient, and these were the largest and smallest eigenvalues. So let's consider F to be the von Neumann entropy. And because for the von Neumann entropy, the Gateaux gradient has this very simple form. If you have this simple form, what can we do? We can invert the relation to write the state sigma in terms of its Gateaux gradient. Okay? So what I had claimed, I did not prove it, but I claimed that the maximizer commutes with the state rho. And here sigma and rho star epsilon are the same. So this means sigma commutes with rho. As a result, L sigma, which depends only on sigma, also commutes with rho, and of course it commutes with itself. So what does this therefore tell us? Let us look at this pi plus minus. They are projections on this and this, right? So this therefore tells us, if these commutation relations hold, that L sigma commute with both of these projections. Why does this help us? It helps us to reduce this relation. Pi plus minus commutes with L sigma, so we can write it, and these are projections, so we can write it in this manner. Okay? So this serves as an eigenvalue equation. So that is for every psi which belongs to this subspace obtained by the action of these projectors, L sigma on psi, just from this relation, is lambda plus minus L sigma on psi. Okay, I hope you all agree. And once you have that, you can use sigma. From this relation, you have sigma on psi, just substitute the relation, and then make use of this. L sigma acting on psi will be this. Okay, so what we see is that when it acts on any vector psi in that subspace on pi plus or pi minus psi, pi plus or pi minus acting on the Hilbert space, it has a constant eigenvalue, lambda plus or lambda minus. And this sigma was the maximizer. Okay, so immediately we know what the maximizer's eigenvalues would be like. It's like this. So on the support of delta plus minus, the maximizer has constant eigenvalues, alpha plus and alpha minus. And of course, in the kernel, they have to have identical eigenvalues. So what do? We take certain number of eigenvalues from the top of the original row and squash it down a little bit, and take some from the below and squash it up a little bit. So you see what we're doing. We're trying to come as close as possible to the completely mixed state, which is the maximum entropy state. But we have to do that under the constraint of the resulting state lying in the ball. And for a prescription of exactly how many to move up and down, the construction is done. And I will ask you to look at the papers instead of in this short talk. And the nomenclature given for the state was, as you can expect, the flattest state because it's closest to the uniform distribution. Alpha plus minus? Sorry. There has to be at least one typo in the talk. Huh? Yeah. Yeah. Okay. Yeah. No, it's right. You lower them to alpha plus and raise them to alpha minus. So, sorry, what were you saying? Okay, that was a mistake. Sure. Sorry about that. Okay, let's talk about some further application. Now, I will actually not talk about it, just mention it, because Eric Hanson will give a poster on it on Thursday, where we prove that not only do we get local continuity bounds, but you can get uniform continuity bounds for a whole family of entropies called the H-phi entropies. And what's interesting is the main key ingredient of this proof is the semigroup property of the rho upper star epsilon, which I stated. But something really interesting is, which I'd like to talk about, is approximate LOCC conversions of bipartite pure states. So, consider pure states, now bipartite pure states, psi rho and psi sigma, okay? And these are the reduced states, rho and sigma. And we know Nielsen's majorization theorem. It tells us that you can convert psi rho to psi sigma via LOCC if and only if rho is majorized by sigma. Now, what happens if rho is not majorized by sigma? We cannot do this, right? This is not allowed. But then a valid question to ask is, does there exist a state which is close to psi rho from which you can go to psi sigma? Or you can also ask, does there exist a state close to psi sigma such that you can go from psi rho to this state? Okay? And we can answer this question as yes using our majorization relation. So let me draw a figure. So here's psi rho and psi sigma, and this transformation is not valid, is not allowed by LOCC. You can't do this via LOCC. And so you ask, is there some state phi close to psi rho such that you can go to psi sigma? Or is there a state close to phi tilde which you can come to from psi of rho? And the answer is yes. And what is this state? It is a particular purification of rho upper star epsilon, which satisfies this majorization relation. That's that state. And here, this is again a particular purification of sigma lower star epsilon, which satisfies such a majorization relation. And what is this epsilon? This epsilon tilde, which is the distance between the pure states, the bipartite pure states, is given by this relation, where epsilon is given by this expression. So here, Ri and Si are the Schmidt coefficients of these two bipartite states, psi rho and psi sigma respectively. And in fact, this expression for epsilon appeared in the paper by Horoditsky et al. In fact, a similar result is also there in the paper by Vandermeer and Werner, where they talk about not LOCC transformations, but catalytic thermal transformations. So this actually a question was partially studied. This bit was studied by Vidal et al. And also by Bosik et al. And in Vidal et al.'s paper, they find the pure state, bipartite pure state, which is closest in fidelity to this state. But the problem there was the state is defined in a very involved manner through complicated recursive relations. Whereas in our case, you saw how simple the states rho star epsilon, upper and lower star epsilon were. So it is extremely simple to say immediately what these particular states are, because we know which particular purification to consider. Okay, so to summarize, we have proved that for rho belonging to D of H and this parameter, there exist these two states satisfying this majorization relation, which is the maximizer and the minimizer for any, respectively, for any Schur concave function. And these are examples of such functions. And this is the bit I hadn't mentioned before. These are the min and the max entropies defined in the following manner. This is the maximum eigenvalue of rho and 2 log trace of square root of rho. So because we have this explicit forms of these rho upper star and rho lower star, we can obtain expressions for these smooth min-max entropies as long as the smoothing is done in the trace ball. This was something which was always a bit of a hurdle before, because you had these mathematical expressions for these one-shot quantities, but you didn't know how to do the smoothing. And these are quantities which arise in one-shot information theory. For example, if you want to consider the smoothed entropy over a trace ball, then it is given by this, because that is the maximum maximizer for the Schur concave function. I also talked about local and uniform continuity bounds for a family of entropies. I mentioned it, and discussed approximate LOCC conversion of bipartite pure states. So before I even go over to the open questions in the last slide, I would like to thank Eric for his wonderful work. We would also like to thank Mark Wilde, and I said I'll say what the story behind this was. So Mark actually had a wonderful conjecture, and that the Lsigma bound, which is the continuity bound for the conditional entropies, he said he thought it can be strengthened, and we were trying to look into that problem. Well, we couldn't solve it, but that's what, along a windy way, led us to the problem studied in this paper. So many thanks, Mark. To Andreas, because he was the one who suggested to us to look at local continuity bounds, and to Hamza Fauzi for his great input regarding convex optimization theory. Okay, do you have 2 minutes for open questions? Yeah, so lots of open questions. So the first question is, everything I presented was regarding the trace ball. So we think it can be extended to other distance measures. For example, a ball in the purified distance, which is usually the distance measure considered in one-shot information theory. But that still remains to be done. Secondly, you will hopefully see Eric's poster. I've already stated this as a very interesting open question, which has remained open for a very long time. We prove a uniform continuity bound stemming from our majorization relation. For example, for the Renyi entropy for alpha between 0 and 1. But a similar result for alpha greater than 1 is outside, cannot be done in the method we use, because we use Schur convexity of a certain quantity, which is not Schur convex as soon as you put alpha greater than 1. And I've looked up the literature, and this has remained an open problem for a long time, and it would be very nice to see how that can be done. Secondly, I've talked about a couple of applications, continuity bounds of the entropy and LOCC conversions, etc. But I hope and believe that there might be more applications of this majorization relation and more significance of these rho upper star and rho lower star epsilon. So there are things still remaining to be done. Thank you.